All right. What do you notice about these sequences?
They're very different from each other.
Okay, that is true.
That's not.
It's true though.
They don't. Well, approximately that way.
What happens in this one?
Doubles.
It doubles each time. What happens in this one?
Third bus. Yeah.
Multiply by thirds every time. What happens in this one?
Oh, it does the switching.
It does the switching thing.
And then
It has the specials. Represents
what? Oh, it multiplies by 2/3.
Multiplies by 2/3. Or you could say multiplies by negative 2/3.
Yeah.
Okay, right? I mean, we already said about the switching thing, but we could say it either way. Okay, so in each one of these three sequences, you said that we are doing what from term to term? We are multiplying by the same number. Okay, that is how you recognize a geometric sequence. Yesterday you recognized arithmetic because we were adding the same number every time. Now we have geometric sequences where we are multiplying the same number every time. Okay, so in your notes, right, you have this definition. Okay, we actually call it a common ratio. And we call it a common ratio because if we take the second term divided by the first term, it's the same as the third term divided by the second term. It's the same as all of that, okay? Even though we feel like we're multiplying by a number over and over, we do call it a common ratio. Okay? Sorry, I wanted to grab my notes real quick. Okay. So, this sequence right here, is this the one that was on the very front? We multiplied by 2 every time, right? All right. So when we go to write the rule, we are going to say our common ratio is 2. Okay. Now, how do we write the rule? This is what you can do right now. Our nth term, so this is the explicit definition. Our nth term is going to be the first term times the common ratio to the n minus 1. Okay. So going back to this example right here, we would write that our first term is 6, our ratio is 2 to the n minus 1 power. Now let's check. If we plug in 1, 2 to the 0 is 1, so we would get 6 times 1. If we plug in 2, we would get 6 times 2, which is 12, so on and so forth. All right, so we're going to do a couple examples, all right, which these are written in your notes for you. All right, in this example, is it geometric? Yes, because we are doing what from term to term? Multiplying by what? It's easier to see over here, isn't it? We're multiplying by 1/3. So yes, you can say, oh, we're dividing each term by 3. Let's go ahead and say that we're multiplying by 1/3 each time. So if we're going to find the common ratio, the common ratio is 1/3, since that's what we are multiplying by. So if we want the explicit definition, we have to first pick out our first term, which is 972 times our common ratio to the n minus 1 power. Now, how would we find the 10th term? Plug in 10 for n. And that is why explicit definitions are nice, right? Because we can find the 10th term, no matter how many terms we have. Okay, recursive definition, not so much. So in your calculator, you need to put 972 multiplied by 1/3 raised to the 9th power. What do we get? Make it a fraction.
4/81.
Why would I say make it a fraction in this case?
0.4938271 is hard to degrade.
That is not the reason.
Is it true?
Okay, our common ratio is written as a fraction. So I want your term to be written as a fraction.
It's true.
I don't know. Okay, recursive definition. Okay, remember, the first term has to be defined. Then the nth term has to be defined. What's happening from term to term? If I have the first term, how do I get to the second term?
Multiply by.
We multiply by 1/3. So we take the term previous and we multiply by 1/3. Take the term previous, multiply by 1/3. That would be our recursive definition. Okay. This is the other one we had on that very first slide. Okay? What did we decide we were multiplying by each time?
-2/3.
Okay, so we did notice, so Maverick said we're multiplying by 2/3 and it has that flip-flop negative thing. Okay? If we have the flip-flop negative and it's a geometric sequence, we can just roll those together and say that our common ratio is -2/3. So what this would look like is that a sub n is 1/2 times -2/3 to the n minus 1 power. And that will take care of both the flip-flop sign and the fact that we are multiplying by 2/3 every time. What? So if this is the 10th term, we're going to take 1/2 times -2/3, we're going to plug in 10. So essentially we have 1/2 times -2/3 to the 9th power. Okay, please find that for me. It won't.
I tried so many times.
Yeah. Okay. Well, sometimes our calculator's not quite as cool as we want it to be. So let's round. Point, negative,
0.01300.
one more.
6.
Okay. Put it into a fraction if possible, but sometimes the number gets so small and our calculator does have to do some approximating sometimes. What? Unacceptable. I'm going to give you 20 seconds to write down the recursive definition and compare it to your neighbors.
Oh, I have fractions.
Your calculator.
Yeah, it's -256 over 19,693.
That's probably why you go to a fraction. And it'll probably say Toby Maguire Spider-Man.
All right, Keegan, our recursive definition.
Son, did you
No,
know that?
Batman was weighted.
Because he's not a superhero. Superheroes are superpowers.
Equals what?
It's true.
Okay, so times the term before it. Okay, and make sure that you, that is a comma, a really big comma. Sorry about that. Make sure you define the first term too. Okay, I know technically we can see the first term, but if I ask you for a recursive definition, I really need it. Okay? All right, so here's another example of when I am giving you two terms, and you have to figure out the formula. Okay? Now, what two things do we need to know for our geometric formula? First term and the common ratio. If we know that the second term is negative 18 and the fifth term is 2/3, what are we going to have to find first? The common ratio. Okay? Now, this is the way that I like to do it. Okay, ready? Our second term is negative 18. How do we get to the third term? Multiply by r. How do we get to the fourth term? Multiply by r. How would we get to the fifth term? Multiply by r. So if we have the second term, we have to multiply by that common ratio 3 times to get to the fifth term. If we divide by 18, we would have negative 1 over 27. We take 2/3 divided by negative 18. Do you agree? Okay. What is R? There. All right, we have a start. Okay. Our nth term is our first term times negative 1/3 to the n minus 1. Now we have to figure out what our first term is. Now this one might be a little easier because we have the second term, but I'm going to show you in general what you would need to do. Okay? We know that if we were to plug in 2, so if we were to plug in 2 to our equation, we would get negative 18. So now we can solve for that first term. So for our a sub n, our explicit definition would be 54 times negative 1/3 to the n minus 1. Oh, is that not what we were asked to do? Find the sixth term. Okay. Well, that would be how you would find the definition. So now that we have it, we can plug in. Sorry, I got so excited to find it. What is it, Eli?
I told him to go.
-2 nines.
That's what I got.
Okay. Now, technically, would we have to find the definition if we wanted the 6th term? We have the 5th term. We could have just multiplied by -1/3, right? But if I gave you the 2nd term and I gave you the 5th term and I said find the 20th term, you would probably want to write the definition, which is why I think I had it in mind that I wanted to do that, so that we knew how to do that. Okay. So that would be the process. Okay. You did a similar problem to this yesterday. Is that correct? Yes.
That sounds roughly correct.
Okay, well, it's in your notes, so hopefully. Now, I did make a mistake, and I did not get this piece written in your notes, okay? Your next 2 examples are finite geometric sums that we actually have a shortcut for. So maybe at the very bottom of your page, write this, and I'm going to give you the shortcut. I 100% apologize for not leaving you room to do
It's okay, this is only going to scrap for the rest of my life.
that. Okay. That's an I.
Okay, well,
No, it's two. Oh, I remember these.
to be fair,
I'm just trying to make it so you can tell that it's not like a line.
That's why I always do the cursive thing. So it's like a little tree that doesn't have any branches on it.
And partial sum. First term times 1 minus r to the n over 1 minus r. Okay? Yeah, it takes a little bit of calculation, but if I ask you to add 7 fractions together, wouldn't you rather do this right here? Yeah. I think so.
Calculator.
And do you have your calculator?
I mean, I do. I'm not sure about on the test, because never mind.
You'll have your calculator. Okay. All right, so you ready for the example? Okay, this is your first example, correct? Okay. So, which partial sum are we finding? The 12th partial sum, because that's where we're stopping right there. So our first term is 4. Then we're going to multiply by 1 minus, what is our common ratio? 0.3. Raised to the 12 over 1 minus 0.3. Please be very careful with how you put this in your calculator. Okay, maybe I should get my calculator up here so we can do it together, huh?
Video can much better.
Okay.
There's many.
So 4 times the quantity, you want to put the numerator 1 minus 0.3 to the 12th all in parentheses, divided by parentheses 1 minus 0.3, or you can just do that in your head, right? And there's our sum. I did. I put it in all at once. Now, if your common ratio is negative, then your common ratio would need to be in parentheses when you are raising it to the 12th power. Or if your common ratio is a fraction, you better put that in parentheses when you raise it to a power. Okay? So for some of this, calculator user order of operations is important. Okay? I would urge you to write down whichever formula you are using on the quiz on Tuesday, just in case you have a calculator error. I can at least know that you have the right process. Otherwise, no partial credit given. Okay? Let's look at the next one. What is our first term? 1. Okay. If you get nervous about it, just plug in that first number right here. 1. So then we have 1 minus, our common ratio is 2. And we're finding the 7th partial sum. What's our sum? 126? 7? Perfect. Okay. Now, if I keep adding numbers onto that series, what's going to happen to the sum?
It's going to get bigger.
It's going to get bigger and bigger and bigger and bigger. Okay? However, let's imagine me this distance away from the door. Okay? And I cut my distance in half. And then I cut my distance in half again. And then I cut my distance in half again. And then I cut my distance in half again. Okay. Technically, am I ever going to get to the door? But is my distance going to be measurable? You know how far away I started from the door? I'm never getting to the door, but I'm getting so gosh darn close, I'm going to be like smushed up against it, right? Theoretically. Okay. If our common ratio is less than 1, we can find an infinite geometric sum. Because of that example I just gave you. Is that exactly what Mr. Beaver did?
I didn't actually start it last.
One year I was like really pregnant when I was talking, and so I did it this way, right? And my stomach it wasn't a good example. So I'll do it sideways now. Okay, we can find infinite geometric sums as long as the absolute value of r is less than 1. And this is how you would do it. You're going to take the first term over 1 minus r. And that's really what you need to remember. Oh, but this should be an infinity, right? First term over 1 minus r. Now, that first term has to be the first term in your sum. So for some weird reason, if your sum starts at 3, then when you plug in 3, that's your first term. That's where you're beginning. Okay? But it's a pretty simple calculation to make. Alright? First of all, it has to be geometric. Second of all, it has to be infinite. Third, absolute value of r has to be less than 1. Otherwise, we're toast. Okay? So let's look at that first example. A, is it geometric?
Yes.
Yes, it is. Okay? It looks slightly different, but notice how n is beginning at 0 And so we have the power of n instead of the power n minus 1. Okay? Is our common ratio less than 1? Yes. Okay? So our sum is the first term over 1 minus r. 5 divided by 1/2 would be your next infinite sequence. Is it geometric? What's the common ratio? Common ratio is 2, which means we cannot find the infinite sum. Because it's just going to keep growing and growing and growing and growing and growing towards infinity. All right, and lastly, yes.
So if you had something like that,
Yeah.
instead of find the infinite sum, could you just put equals infinity?
I mean, yeah, that would be fun. Yes. Yes. Okay. This example is it geometric? Yes. Our infinite sum. We're going to take our first term. Oh, can we find it? It's because it's the absolute value of r less than 1. Okay? Times over 1 minus r. Please be careful. This is 1 minus negative 1/4. So we basically have 1/3 divided by 5/4. What's our infinite sum?
4/15.
Okay. So do you remember on Wednesday, our very last example was a geometric sum? We didn't know it was geometric, but it was. Go ahead and turn to that last example from the first page, or like the back of the first page. Okay, we added 3/10 plus 3/100 plus 3/1000 plus 3/10,000, and we ended up getting 0.3 repeating, right, which was 1/3. Okay. Our last example is determining what number 0.59090909090 repeating is. How are we going to do that? What are we going to have to use? Okay, so you a pretty big hint. What kind of sum are we going to have to think about? Geometric. Okay, that 0.3 repeating was the sum of a geometric sequence. Okay, so here we have 0.5, but then blah, 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 right? So let's go ahead and write this as 0.5, because we know what that is, right? Plus 0.090909 repeating, right? Okay, so let's talk about how we would write this as a series. Okay, what would this first term right here be? .09. What would we write? 9/100. Okay, and then we could add . Oh, I should really like this. Okay. Let's think about it like this, so we can visually see it, okay? This is like 0.09. plus 0.0009 plus 0.000009, etc. Right? To get that decimal, we would have to add those decimals all together. So we have 9/100ths. This would be 9 over what? 10,000? And this would be 9 times that's like 9 million, right? Okay. What's our common ratio then?
1 over 100 to the n.
So what we have is we have the sum from n equals 1 to infinity of our first term 9/100ths times our common ratio 1 over 100. Okay. Well, we can find an infinite geometric sum by taking the first term over 1 minus r. We have 9/100ths over 99/100ths. What would that reduce to?
111.
We have 1/2 plus 111. What? 13/22 is what that decimal is. Isn't that cool how we can work backwards like that?
Sure.
Numbers are awesome.
I'm sure.
Probably not. If it's a repeated fraction, your calculator's not going to be of much help.